Hello, dear students. I am Samir Velankar. I welcome all of you to this another video of graph data structure. In this video, we will be learning to traverse a graph. The topic is graph traversal. Now, given a graph, as you see here, there are 6 vertices in this graph and it is undirected, not weighted. There are no weights to the edges, as you see. None of the edges are having weights and none of the edges are having direction. So this is undirected and not weighted graph. Now we want to traverse this graph. By the way, you already know meaning of traversal. We want is we want to go to every vertex of the graph and we want to print the information stored in that vertex. Here, typical information is the vertex number. But remember, traversal means reaching or visiting every vertex exactly once. We don't want to print any vertex more than once. Neither we want to miss out any vertex. Now there are two ways in which the graph can be traversed. Like there are three ways in which trees can be traversed. Binary tree I'm talking about. Binary tree can be traversed in order, pre-order and post-order. Like that, there are two methods by which you can traverse a graph. First method is depth first search DFS traversal and second is breadth first search BFS traversal. Of course, I have not written the algorithms of DFS and BFS in this video. We will be just looking at the procedure. We can use this procedure manually to trace the DFS or BFS of the graph. Let's consider this graph containing 6 vertices. What will be the procedure for DFS, depth first search? Let's see. Now, typically we start traversing the graph from vertex 1, but there is no such rule, remember. You can start traversing the graph from any vertex because graph is not characterized with some root node or topmost node. So, some beginner, some person who is tracing DFS can even start saying that sixth vertex is from where I will start traversing the graph. But in our examples, we will be always traversing the graph from first vertex. What we do is we go to the first vertex and we visit it. Now, by visit, what we mean is we process it. By the way, by process, what we mean here is that we will print it. So, the DFS traversal is going to print first vertex as vertex 1. Now, once we print the vertex 1, we mark that vertex as visited. A typical tick we put. But in computer science, there is nothing called tick. Now, later in our videos, where I will explain the algorithm, we will see that we will use something called visited flag, which can be 0 or 1. So, initially visited flag for first vertex will be 0 as it was not visited. But as soon as you visit it, that means you print it. We will make visited as 1. That means we have ticked that vertex 1. Anyway, don't bother about the algorithm right now. Okay, so now we have printed vertex 1. What do you do next is we check which vertices are adjacent to 1 now. Who are the neighbors of 1? Now you see in this graph, the neighbors of 1 are 2 and 5. That's it. 2 and 5 are neighbors of 1 or adjacent vertices of 1. Then we take among the neighbors of 1, 2 and 5 are the neighbors. Among the neighbors of 1, we take that vertex which is least numbered. Now among 2 and 5, which are neighbors of 1, 2 is the least numbered vertex. So we consider this vertex first. And there is one more criteria. The vertex that we are considering should not be visited already. Now you can see this vertex 2 is not yet ticked, it is not visited. So what we do is we decide that we are going to visit 2 and we print 2. So the second vertex visited or printed is 2. As soon as we print 2, we will tick it. we will mark it as visited. So just a quick recap. We started printing 1. After printing 1, we ticked it, visited. Then we saw who are the neighbors of 1. Neighbors of 1 are 2 and 4, 2 and 5. Consider the least neighbor. Least neighbor is 2. Check it is not visited. So you print 2 and then you tick it as visited. Now comes the fun part. After printing 2, any beginner might feel that the second neighbor of 1 was 5. So after 2, 5 should get printed. But there is where depth comes into picture. After printing 2, you just forget all other neighbors of 1. Actually, there were two neighbors of 1, 2 and 5. We printed 2. After printing 2, you consider this second vertex, vertex 2, and repeat the process on vertex 2. What it means is, you see the neighbors of 2 now. The neighbors of 2 are 1, 4, 3, and 5. Lot of neighbors. Among these 4 neighbors, 1, 3, 4, 5, you take the least numbered. The least numbered neighbor is 1. I'll write it here better. We are considering neighbors of vertex 2, which are 1, 3, 4, and 5. Among these neighbors, consider the least numbered neighbor, which is 1. But 1 is already visited. You can see it is ticked. So don't consider 1. Don't consider the vertex which is already visited if it is in the neighbor list. But then check the next least neighbor. Next least neighbor is 3. You can see among the neighbors of 2, 1 was least neighbor was visited. So you consider the other adjacent vertex, which is 3, and 3 is not ticked. So you decide that you are now going to process 3 or visit 3. After printing 3, you tick it as visited. Now you repeat the process on third vertex. Look how you are not considering other vertices which were neighbors of 2. Actually, 4 and 5 were also neighbors of 2, isn't it? But as soon as you print 3, you now consider vertex 3 and repeat the process on 3. So what do you mean by repeating the process on 3? You see the neighbors of 3. Now neighbors of 3 are 2, 4 and 6. So we are considering neighbors of 3. Check that. Neighbors of 3 as seen in the graph are 2, 4 and 6. So considering the least neighbor, which is 2, but observe 2 is already ticked. It is visited. So don't consider the visited vertex, but see the next least neighbor, which is 4. And as 4 is not yet visited, you decide that from 3 you are going to jump to 4. And 4 is visited, so it is ticked. Now consider 4 and forget all other neighbors of 3. If you now consider vertex number 4, what will you do? It is already printed as you can see and visited. If you consider 4 now, then see the neighbors of 4. Check the adjacent vertices of 4. Now adjacent vertices of 4 from the graph are 2, 3, 5 and 6. Check the graph. Take the least numbered neighbor, which is 2, but it is visited. So don't consider 2. Check the other least number, which is 3, but 3 is visited. Don't consider it. Check the next least numbered neighbor, which is 5, and 5 is not yet ticked. You can see the picture. 5 is not yet visited. So you decide that from 4 you are jumping to 5. So 5 is ticked. Now after visiting 5, you repeat the process on 5. So repeating the process on 5 means see who are neighbors of 5 now in your graph. If you see them, neighbors of 5 in your graph are 1, 1, 2, 4, and 6. Now, among these neighbors, 1 is least neighbor but visited, so cancel out. 2 is least neighbor, next least, but visited, cancel out. 4 is next neighbor, least neighbor, but visited, cancel out. 6 is the next least neighbor, which is not visited. So you print 6 and mark it as visited. Okay, now what would you do? You have just now printed 6. So the process says after printing 6, repeat the process on 6. That means you will see the neighbors of 6. As you can see, it is so easy to see in this graph that you are now seeing neighbors of 6, but all the neighbors, whatever name, I am not even writing the neighbors of 6, but whoever are the neighbors of 6 are visited. That means you cannot jump from 6 to any other new vertex. Such a vertex for which all the neighbors are already visited is called dead end. Sixth vertex in our example is a dead end because all the neighbors of 6, which are 3, 4, and 5, are already ticked. So you just can't jump from 6 to any new vertex. So what you do whenever you come across a dead end in DFS, you just backtrack. You just go back exactly to that vertex from where you came to 6. Now this is something tricky and you may have to remember. Last time when you came to 6, from where did you come to 6? Well, you came to 6 from 5. Recall when we were checking neighbors of 5, we got 6 as the neighbor and we jumped there. So we just backtrack. We will backtrack to 5. Just backtrack to 5. When you are back at 5, you repeat the process on 5. Be careful, be careful. When you are back at 5, you repeat the process on 5. That means you ask, hello, fifth vertex, do you have any neighbors which are not yet visited that can be printed? So, fifth vertex, can we jump to any other vertex which is not yet visited from 5? But the answer you will see is that whoever are the neighbors of 5 are already visited. That means 5, fifth vertex, is also a dead end. I hope you are understanding. You cannot jump to any new vertex from 5. So now you will go back to the vertex from where you came to 5. This is something that you will have to remember in the process. Well, you came to 5 from 4, from 4. So you're back at 4. And when you are back at 4, you will see 4 is also dead end. I hope you understand straight away. Because 4 does not have any neighbors which are not visited. If you come to a dead end, you will backtrack to the vertex from where you came to 4. So you will backtrack to 3 because you came to 4 from 3. But you observe that 3 is also a dead end. All the neighbors of 3 are already done, already visited. So 3 is a dead end. So you will jump or backtrack to 2 because you came to 3 via 2. Easily 2 is a dead end because all the neighbors of 2 are already done. So you will backtrack to 1 because you came to 2 from 1. So you are back at 1. You ask 1, is there anything adjacent to 1 which is not yet visited? But 1 will say, no, I don't have any neighbors which are not visited. So 1 is a dead end. And if 1 is a dead end, and you remember the process started at 1 and 1 itself is a dead end. Remember, DFS was started from vertex 1 and 1 itself is a dead end. Then DFS halts, stops. So the output of this DFS is 1, 2, 3, 4, 5, 6. Okay, let's see. I'm drawing the same graph. 1, then 5, then this will be too good. Let's see what I am up to and why I am drawing this graph again. This was the graph given. Here was the vertex 6 and these were the adjacencies. Now just imagine 1 is also adjacent to 7. I'm just extending the graph. 7 is adjacent to 8, and 8 is adjacent to 1 and 7. This is the graph. Now, what would be the DFS? Have patience, just check the DFS. We'll start printing 1, mark it as visited. Then see the neighbors of 1. Who are the neighbors? Neighbors of 1 here are 2, 5, 7, 8. 4 neighbors. We consider the least neighbor, and least neighbor 2 is not yet visited. So you will print 2 and mark it as visited. Now you be with 2 and you repeat the process on 2. Forget about all the other neighbors of 1. So if you visit 2 now, if you process 2, who are the neighbors of 2? Just check, neighbors of 2 are 1, but it is already visited. 3, yes, this is the least number neighbor among 4 and 5. So 3 will be visited next. I hope you got it. So 3 is marked and 3 is printed. Similarly, from 3, you will go to least numbered neighbor, which is 4. 4 is done. From 4, the least numbered neighbor is 5, which is not visited. 5 is done. From 5, the least number neighbor is 6. 6 is done, but 6 is a dead end. No neighbor of 6 is now pending. So you will go back to 5. You will be back at 5. 5 is a dead end. You can see all neighbors of 5 are already done. So you will be back at 4. 4 is a dead end. Back at 3. Check that 3 is also dead. 2, 2 is a dead end. Back to 1. Now, importantly, 1 is not a dead end. When you will come back to 1, you will ask 1, do you have any neighbors pending that we did not consider last time? Now, among the 4 neighbors of 1, which were 2, 5, 7, 8, 2 and 5 are visited, but the next least neighbor is 7. So we will visit 7 and we will print it and mark it as visited. Now we repeat the process on 7, and least number neighbor of 7 is 1 and 8, but 1 is visited. So 8 will be visited. 8 is marked. But now 8 is easily a dead end. All neighbors of 8 are visited. So you will be back at 7. 7 is a dead end. Among all the neighbors of 7 are done. And you will be back at 1, backtrack at 1. But 1 finally is dead end. And the process started at 1. So DFS ends. This is the DFS traversal of the given. I hope you got this, got the idea of DFS, how DFS works. So let's see, before we see BFS, let's see DFS on this graph. This is a directed graph. Every edge has a direction, but there are no weights. So this is directed and not weighted graph. And let's do DFS. Let's not concentrate on BFS here. What is the DFS output of this graph? Let's see. Start at 1, print 1. Mark it as visited. Keep checking. Now after printing 1, see the neighbors of 1. Now the neighbors of 1 are easily, because 1 is adjacent to 2, there is a directed edge and 3. So among these neighbors, we will be taking least numbered neighbor, which is 2. And then we will forget about other neighbors of 1, but we will mark 2 as visited. As you see, we will mark 2 as visited and repeat the process on 2. So if we repeat the process on 2, what do? We see the neighbors of 2, isn't it? Is 2 adjacent to any vertex? You can see 2 is adjacent to absolutely no vertex, because there is no directed edge from 2 to any other vertex. So 2 does not have any neighbors. Although other vertices are adjacent to 2, but 2 is not adjacent to any vertex. Then easily 2 is a dead end. And what do you do whenever you encounter a dead end? You simply backtrack to the vertex from where you came to 2, isn't it? You came to 2 from 1. And when you are back at 1, you ask the vertex 1, okay, do you have any vertex which is still pending and is in your neighbor list? Yes, one will say 3 is my neighbor. And now among all the neighbors, this is the least numbered which is not yet visited. So you will easily print 3 and mark 3 as visited. I hope you are getting DFS very well. Now what? After printing 3 and marking it as visited, we will process 3. We'll see neighbors of 3. And the neighbors of 3 are 2. You can see neighbors of 3. 2 is a neighbor and 4 is a neighbor, isn't it? Now among them, 2 is visited, least numbered. So next is 4. So 4 is visited and marked. No, 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 the process doesn't end here. Technically now we repeat the process on 4 because we have just now printed 4. So who are the neighbors of 4? Only 3 is the neighbor of 4. But 3 is already visited. So 4 is a dead end. And what will you do then? You will backtrack to 3 because you came to 4 via 3. So if you are back at 3, you will repeat the process on 3. But 3 is also a dead end because all the neighbors of 3 are done. So you will backtrack to 1 because you came to 3 from 1. If you come back to 1, 1 itself is a dead end. Isn't it so? And you can easily see that if 1 is a dead end, the process halts. And this is the DFS. This is the DFS for the given graph. Okay. Before we close the video, I will draw some arbitrary graph. Believe me, even I don't know what I am drawing. So suppose we have an undirected graph somewhat like this. Just check. This is the graph we are having. Okay. So what will be the DFS of this graph? Print 1, mark 1 as visited. Right? See the neighbors of 1? Neighbors of 1 are 2 and 3. Only 2 and 3 are neighbors. Take the least numbered, which is not visited, that is 2. Mark 2 as visited. Okay. Forget about other neighbors of 1. Now you be with 2. Repeat the process on 2. Who are the neighbors of 2? Check neighbors of 2 are 1 and 4. But among these neighbors, take the least numbered neighbor, which is 1, but 1 is already visited. So you consider the other least numbered neighbor, which is 4, and mark 4 as visited. Now repeat the process on 4. Among the neighbors 2, 5 and 6, see the neighbors of 4, 2, 5, 6. 5 will be visited because it is least numbered and not visited. Mark 5 as visited. Clearly now when you repeat the process on 5, 5 is a dead end. You cannot jump to any non-visited vertex from 5. So you will backtrack to 4. Well, after backtracking to 4, you can go to 6, you observe. Among the neighbors of 4, 6 is pending. So 6 is visited next and marked as visited. Once at 6, 6 will take you to 3 because the neighbors of 6 are 3, 4, 7, 1. Properly reading it, neighbors of 6 are 1, 3, 4, 7. But one least numbered is visited. Then, neighbors of 6. We are talking about neighbors. Neighbors of 6 are 1, 3, 4, 7. 1 is visited, 3 is not visited. So we will visit 3 and mark it as visited. Needless to say, 3 is a dead end. All the neighbors of 3 are done. Neighbor of 3 is 1, which is done. Neighbor of 3 is 6, which is done. So we will backtrack. Where will you backtrack from 3? Yes, backtrack to 6. You came to 3 from 6. But when you will be back at 6, you will see 6 is not a dead end. There is one neighbor of 6, 7, which can be processed. So we mark 7 as visited. Clearly, when you repeat process on 7, 7 is a dead end. So you backtrack to 6 because you came to 7 via 6. When you are back at 6, you will see that 6 is dead. All the neighbors of 6 are done. And you recall you came to 6 via 4. So 4 is also dead. You can see all the neighbors of 4 are done. And then you will backtrack to 2. I'm sure you are getting it. Because you came to 4 from 2. 2 is dead. All the neighbors of 2 are done. And from 2 you will backtrack to 1. But 1 is also done. This is dead. All the neighbors of 1 are done. And you started the process at 1 and 1 itself is dead end. So you stop the process of DFS and you say this is the output. Okay, the cautious and attentive readers and listeners might have understood that DFS procedure or function, DFS function is going to be recursive. It will be a recursive. Inherently, it is a recursive function. Think over it. Anyway, we are going to see that recursive function where we will reason out why DFS is inherently, it should be recursive function. Although we can write non-recursive version of DFS also. Any recursive function can be written as non-recursive and vice versa. But DFS is best written using recursion. Anyway, we will see BFS in the next video and algorithms in next to next video. Thank you very much.